So we're going to go ahead and get started for the evening. So welcome to the August meeting of the Tucson Amateur uh, Astronomy Fundamentals Special Interest Group, otherwise known as AFSIG. I see several names I don't recognize on the call, which is always good to have some new people or people who maybe just attended frequently and I don't remember their names off the top of my head. So tonight, we only have one presentation lined up. There was a scheduling miscommunication. So Stephen's presentation will be deferred to next month. I believe he will be giving a presentation on the James Webb Telescope. So look forward to that. And without any further ado, we're going to go ahead and get right into it. Let me organize some things. So turn off PowerPoint captioning subtitles because that's annoying. Don't know why it does that. Laser pointer. So bulk of this presentation is divided into a couple of different parts. The majority of it will be spent talking about the various components of a solar eclipse. This includes all the varieties, not just the total solar eclipse. So annulars, hybrids, and partials. Then we'll briefly touch upon some of the distinctions between the different types of solar eclipses, which I just mentioned. We'll also highlight the two upcoming solar eclipses here in North America that are coming up this October, and then again next April. Some minor information if you weren't already looking at some of that and some things you may want to consider. And then we'll finish it off with some eclipse viewing safety tips, which is kind of obligatory because the sun is bright and dangerous. So for those who follow some of the more professional astronomy announcements, you'll see a couple of different terms come up occasionally, especially for those that are familiar with exoplanet hunting. We'll see terms such as transit or occultation get brought up, and there are relations between those two as well as eclipses. The main difference being is pretty much, as we might say, a matter of where the observer is. So a transit, and this will make more sense. There's a diagram on my next slide, so just hold on first of all. A transit starts off with a smaller object that is closer to an observer, and that smaller object is moving across the face of a larger object. For example, for those that look at the Galilean moons, every time you see a Galilean moon moving across the face of Jupiter, that is a transit. When you an occultation is when a smaller object is farther away from the observer and moves behind a larger object. So, for example, when on the rare chances it happens when Venus goes behind the moon, this is an example of an occultation. And an eclipse is simply the shadow cast by a celestial body as it onto some other object. So kind of a better idea here. So as we can see, kind of right in front and center, here's an example of a transit. You have this smaller object, for example, the moon or Mercury. Mercury would be considered, and we'll say that this larger object is Jupiter or the sun, and it is moving across the face of this larger object from our perspective, from where, if you're looking at this slide out. The eclipse over here on the left is simply just the shadow that's moving across. So it's distinctly referring to the shadow cast by the object. And then an occultation is seen briefly over here, where this smaller object is going behind the larger object. One of my favorite comics is XKCD, and I will have a couple of these sprinkled out the presentation, mostly because I find them funny. So this is a diagram. If you were to see the shadow cast by other objects in our solar system, like, say, Jupiter, showing their relative sizes compared to everyday objects. On the left-hand side, we see the shadow of the moon as cast on the Earth, in this case, using London as an example. And on the right, we have a soccer field in this corner. And if you could see them, followed by the shadows of the various planets in our solar system. So if you could somehow see the shadow that Venus cast on the Earth, it's actually quite large, probably the size of a couple football stadiums. So it's always nice to see different things into perspective. So eclipses are driven, from our point of view, are driven by what's known as the Saros cycle. It refers to a periodicity of the Earth and the moon's orbits with respect to each other. This cycle defines a series of solar and lunar eclipses, and it repeats every 18 years. So at the beginning of a second Saros cycle, you will see an eclipse very similar to one at the beginning of the first Saros cycle. So it's just a repeating pattern in the orbits, which makes these eclipses very predictable. Interesting though, the Saros cycle is not in sync with the Earth's rotation. It's out of alignment by about 120 degrees, which means that the pattern of eclipses shifts about 1/3 of the 120 degrees with respect to where they were previously. It's a little bit off more than that, just because there's some accuracy in here, but to give you an idea. So for example, the next time, if for those who are familiar with the 2017 eclipse, the path of totality for that eclipse, when it next would come up, would appear in the next Saros cycle, will have shifted 120 degrees and put it, I think, somewhere over the Pacific. So the whole eclipse phase just completely shifts. The regularities in this average about having two eclipses. Two eclipses. I think it includes solar and lunar. I should have clarified that, per year. And as I mentioned, they'll have, if you separate them by the Saros cycle, two eclipses at the same time in a Saros cycle will have the same duration, and they'll be the same type of eclipse, etc. They just won't be in the exact same position on the Earth, which is why we never get to see a solar eclipse every 18 years in the same location. From there, we jump over to the various components of the eclipse. It's, from our perspective, it's just there are three main elements that will come up, not counting the moon and the sun, but they are collectively the penumbra, the umbra, and the antumbra, with the antumbra being distinct to annular solar eclipses. That is not a part of total solar eclipses. All three of these terms are derived from Latin, with the umbra being the darkest inner shadow. And this part of the shadow forms the path of totality during a total eclipse. This is the path of totality, or the path of annularity, is where all the action happens. If you are not on this path as the eclipse occurs, you won't get to see all the pretty things that happen. From there, we have what's known as the diffuse the penumbra, which is the diffuse outer shadow. This is the portion of the shadow that is responsible for the partial eclipse phases. So if you are seeing a partial eclipse, you are standing on or near the penumbra. And then the last component is the slighter outer shadow, called the antumbra, which distinctly means beyond shadow. And it's a slight extension of the umbra. Again, that main dark portion that forms the path of totality. But this is the variant of it that appears specifically for annular solar eclipses. So you are seeing, when you are in the path of annularity for an annular eclipse, and that is a mouthful to say, you are standing in the antumbra shadow. So the top diagram here kind of gives you an idea of what specifically we're referring to. So we can see here's the moon. This is for an annular solar eclipse. We have this dark cone coming off the moon. In the center, this is the umbra shadow. We have this larger, more diffuse cone for the penumbra, which is where the partial eclipses are. And then if you see it might be hard to see depending on your screen size, but right here at the end of the penumbra, there is a second cone that sort of just spawns off of it. And this is the antumbra, hence its name, beyond shadow. So it's beyond the full shadow of the moon. I'm not quite familiar with why this occurs. I'm sure if I had some more time, but interest. So the distinction here, this is specifically for annular solar eclipses. In a total solar eclipse, we have it so that the moon does not cast an umbra shadow at all, an antumbra shadow at all. It is too close to the Earth, although it is enough to fully eclipse the sun. It is not far enough away that it'll actually cast the antumbra shadow. So if this was if the Earth was transparent, you'd actually see the antumbral cone being projected deep inside. Questions so far? Kind of moving along. I need to check to see if there's nothing in the chat. Cool. Okay. Again, with some XKCD comics making fun of various things. If there are any Lord of the Rings fans in the audience, this is a play on words with the horse Shadowfax being pronounced fact. So we've talked about what distinguishes a solar eclipse, not a solar eclipse, an eclipse from other types of orbital movements. We talked about some of the main components that we observe from the ground. But now we're going to jump over to some of the more interesting phenomenon, which are still really cool to go look at. These are what are known as diamond ring and Bailey beads. These are features specific to solar eclipses that occur as the moon transits the sun. Again, because an eclipse is a transit. We're just they are generally not safe to view without eye protection. You will want to have a solar filter on any binocular or camera or telescope lenses, or be wearing appropriate solar eclipse eyewear. And they, as I mentioned, they only occur during total eclipses or annular eclipses. You won't see these in a partial eclipse usually, just because of how they occur. And they are primarily resolved by various features on the lunar surface. We are, as you know, we've seen in Apollo pictures, the moon is not a perfect sphere. It does have hills and valleys, and those are responsible for forming these two very specific features of solar eclipses. So this is an example of Bailey beads. You can see them right down here in the bottom right corner. It's this small bright blob, looks kind of like an elongated bean hanging off to the side of the larger, brighter edges. So it's these little small spots. And then the example of the diamond ring is aptly named so because you get a giant bright spot of the sun, of bright solar light coming through during the portion of a total eclipse or an annular eclipse. You'll see these occasionally. So jumping over to a brief question, what do you think the longest possible duration one can observe totality or annularity is for a solar eclipse? Any guesses?
4 minutes.
For the upcoming October total eclipse in April, that is correct. But in general, if you on any solar eclipse, what is the longest possible time? So, if you were on the ground, the longest possible period of totality for a total eclipse is about 7 minutes and 32 seconds. And for annular eclipses, the longest period of annularity is about 12 minutes and 30 seconds. If you aren't moving, if you're just staying stationary on the Earth. Some people like to cheat, though. Specifically, in 1973, there was a group of scientists who hopped in a Concorde jet and followed a solar eclipse along the path of totality for about 77 minutes, which unlikely to happen anytime soon. But more recently, the longest solar eclipse that was visible on Earth was the 2009 solar eclipse that went through Central Asia, which had a period of totality of about 6 minutes and 39 seconds. We'll talk more about the period of totality for the upcoming North American eclipses near the end of this presentation. So mentioned both of these terms quite a bit now at this point, totality and annularity. So these are the points in time where the moon fully eclipses the sun. I put quotes around fully because in an annular solar eclipse, the moon does not fully cover the face of the sun, hence its specific name. And you can only really experience these two phenomenon when you are inside the umbra or antumbra. As I mentioned several times, if you are outside of this shadow, you'll just see a partial eclipse. You won't get the full effect. And the path of totality or annularity is about 160 kilometers wide, which is averages about 100 miles. It changes slightly depending on the type of eclipse. So in an annular eclipse, we'll typically have a slightly wider path of annularity just because of, again, the moon is slightly farther away. It's closer to the sun, so the shadow will spread out more. While a total solar eclipse will sometimes have a smaller path of totality just because the moon might be slightly closer. And because of the orbits, this path of totality will always move from west to east. This is the only real complicated number I'm going to have throughout this presentation, and that's the eclipse magnitude. This is one of several statistics that sometimes get reported about solar eclipses. It's just a way to describe and as a short summary of what the eclipse experience might be like. It is a ratio or percentage of how much of a celestial body is being eclipsed. So this number can be applied both to lunar eclipses and to solar eclipses. For our purposes, this is just a number that's saying how much of the sun is being eclipsed by the moon. This value is always reported at the point of greatest eclipse. So since the moon's orbit is not a perfect circle, the total time of totality will change at different points along the line in which it moves across the Earth. At the beginning of the solar eclipse, it will be a shorter point of shorter total time of totality compared to the center point of the eclipse generally. So Eclipses that have a eclipse magnitude of greater than 1 are typically total eclipses. Oh, not typically, are always total eclipses. So interesting. You're maybe thinking, why can this ratio be greater than 1? What does that mean? So when the eclipse magnitude is greater than 1, it just simply means that the moon is covering more of the sun than we can see. So the moon, this makes it essentially, since the sun will be smaller with respect to the moon from our perspective, it just means it's covering much more of the sun. Questions on that? It needs a visual, and I unfortunately don't have one that can show it better. Well, maybe on the next slide. Wow. If the eclipse magnitude is less than 1, this is always a annular eclipse or a partial eclipse. Unfortunately, there isn't really a relationship between the eclipse magnitude and how long totality or annularity is. This is just a number describing how much of the sun is being eclipsed from our perspective. For example, our upcoming eclipse here in October has an eclipse magnitude of 0.952, which is, as a percentage, it just tells us that 95% of the sun will be fully eclipsed by the moon if you are standing at the point of greatest eclipse. For those who are interested, NASA has a good series of tables that just summarize all of this information for the next 300 years of stellar eclipses. If you want to go take a look at that. So here is again a slide kind of trying to relate the magnitude here. So up here on this top line, you see that this is an eclipse magnitude of greater than 1. So we get a total solar eclipse. So if you look here in the center point, you see that this orange circle here representing the sun and the dark circle representing the moon. So this gives you kind of an idea of what's going on when it's greater than 1. So instead of being an exact circle to circle match, the sun's circle would be slightly smaller with respect to the moon. While down here for an eclipse greater than 1, it's an exact matchup. Sorry, an eclipse magnitude of what? Exactly 1. And then for an eclipse magnitude of less than 1, we get the inverse, where you see the sun because the moon doesn't fully eclipse the surface. We'll talk more about these, the first contact, second contact, and so on later on. So any questions on any of the components of solar eclipses before we move on? That is kind of a lot to digest in a short time frame. Okay. So moving right along to the various types of eclipses, we'll briefly come through each of these. The more common of the two of the varieties, excuse me, not two, there's 4, are partial eclipses. Every total eclipse and annular eclipse has a partial eclipse component to it, but you can also have standalone partial eclipses where because of the Saros cycle, you will only ever see a partial eclipse. As we mentioned, the moon doesn't perfectly line up with the Earth and Sun at this point. It's kind of pretty obvious. And these are generally the easiest to observe because the umbra shadow is generally much larger than the penumbra shadow is much larger than the umbra shadow. So this is visible to much more observers. And gives it a lot wider audience, although it will require eye protection at all times, just the sun is bright and dangerous. An example of a partial eclipse, for those who may not have seen one, just to give you kind of an idea. So in this case, how this works out is the moon might actually be moving along this line from left to right in this picture, so this portion of the sun would never get fully eclipsed. That's why it will always remain a partial. Conversely, during a total annual eclipse, the moon would presumably be moving from bottom to top, so it would cover almost the entirety of the sun. This is kind of just give you an idea. The next big type of solar eclipse is what's known, as we've mentioned, is an annular solar eclipse. It gets its name from the Latin word annulus, which conveniently means ring, hence the common term you will see for these eclipses as the ring of fire eclipse. The distinction between these is that while the sun, moon, and the earth do line up to form an umbra shadow, the moon is too far away that it doesn't that the umbra shadow never reaches us, so we don't see a total eclipse. Like partial eclipses, you should be wearing eye protection for these at all times. Even though for example with the upcoming October eclipse, the moon eclipses 95% of the sun, that remaining 5% is still enough to blind you if you stare at it for more than a few seconds or without proper protection. So kind of segueing here back to some terms we saw on a picture a second ago, are the various eclipse stages. These apply both to annular eclipses and to solar eclipses. They're typically referring to, they are aptly named the first contact through the fourth contact. And these are simply referring to the points where an edge of the moon moves out of one side of the umbra or penumbra shadow. This will make a little bit more sense when I show a picture next. So, for example, in the first contact stage of an annular solar eclipse, the moon, the first edge of the moon, will first contact the sun. So that's the first contact. The second contact is when the sun has moved completely across the face of the sun, so that leading edge is now matching up with the opposite side. This is the point in which annularity or totality is at its begins. This is where you get to see all of the cool things. For an annular solar eclipse, this is where you'll see the prominent ring of fire. For a total solar eclipse, this is where you'll be able to see the corona of the sun, as well as some interesting other things you might see on the ground with chirping birds and that are freaking out. The third stage is the maximum eclipse. This is the point where the sun's disk is maximally covered by the moon. This is the point of where you would this is the point where the area around where the shadow is creates the darkest shadow, if that makes sense. So it's basically you're standing at the center point of the shadow at that point in time. After that is the third contact. This is when the annular eclipse starts moving off the face of the sun. And you will notice, like here with the third contact, as well as the second contact, these are the 2 points where you are most likely to see the diamond ring or the Bailey bead effect. And then at the end of that, we have the fourth contact stage, which signifies the end of totality or annularity. And the end of the eclipse, the complete end of the eclipse. This is including the partial phases. Excuse me, I'm messing that up. So once fourth contact has been reached, that's it. That's over. You go back to your car and drive safe. So to kind of signifying that again, here with this diagram. So here's first contact, where you can see here the moon and the suns have one edge that meets. This is the beginning of the partial eclipse phase of that particular eclipse. And then it moves into the second contact. This is where the opposite side of the sun is now reached the opposite side of the moon, the same leading edge of the moon. So they're fully covered. This is so again, the second point of contact with the sun from edge to edge. Then we have greatest totality here in the center. Then third contact is where the opposite side of the sun is reaching the opposite side of the moon. So it's starting to move off. And then at the end of that, we have fourth contact, where the sun and the moon are no longer eclipsing each other in any way, and that's the end. A slightly out of focus image. I unfortunately do not remember where I got this one, so I leave this uncredited. This is, as we can see, this is an example of an annular eclipse with the whole ring of fire. So this is an example of what we will, with good weather, what you might experience in the upcoming eclipse this October. From there, we go to total eclipses. This is where, unlike the annular eclipse or the partial eclipses, this, again, getting its name, the moon disk will cover the entire surface of the sun from our perspective. It is only during totality in a total solar eclipse that you do not need eye protection at all, because the sun is covered completely. It is safe to look at the moon and the sun during this time, and is actually fully recommended because it is quite a sight to see. This is also the only point where we are able to see the solar corona, which is the hot stream of solar particles that are leaving the surface of the sun. This part eventually forms part of the solar winds. So this is also a slightly out of focus image, but for those of us who saw the 2017 solar eclipse or any of the solar eclipses that have occurred since then, this is a rough idea of what you can expect. And yes, it does really look like this, even to the naked eye. It is quite fantastic. It's probably the most spectacular of the types of eclipses that you can go see. And then the last one, this is the fourth type, is a hybrid solar eclipse, which is where an annular eclipse or a total eclipse transitions into the opposite. For example, you might have an eclipse may start at one point along the path of totality as a total eclipse, and then at some point transition into an annular eclipse. Or the opposite can happen, where the eclipse begins as an annular eclipse and then transitions into a total eclipse. The most recent hybrid eclipse was actually this April. The solar eclipse that went through the Australian and Pacific Islands was in fact a hybrid eclipse, although the majority of that eclipse was unfortunately over water. So, as I briefly mentioned, the hybrids are the rarest type of eclipse. So this is basically a summary table showing all the solar eclipses that have occurred in the last 5,000 years, from 2000, over the last 4,000 years, plus up to the year 3000. So from 2000 BC to the 3000 CE. As we can see, only about 5% of all solar eclipses will be a hybrid eclipse. So these are very uncommon. If you do get the chance to go see them, it's not a matter of you'll see both eclipses at one spot. Since the transition occurs over the path of totality or annularity, you'll only ever see one or the other during a hybrid eclipse. You won't see at if you're standing on one surface of the Earth, you won't see a total eclipse, and then 2 minutes later see an annular eclipse. Unfortunately, it does not work like that. But you can also see that partial eclipses and annular eclipses are almost roughly equal to each other in terms of frequency, with about 2/3 of all eclipses being either a partial eclipse or an annular eclipse. So, and now for the good portions, any questions or comments before we move on to the upcoming eclipses here in North America? Okay. So first on the list is the upcoming annular eclipse this October. It is on October 14th, 2023. It will begin over Oregon, is where, if you are on land, there are generally cruise ships that will take you into the path of annularity or totality. There are some members of the club who I know are doing this. But it begins over Oregon and it ends off of the coast of Brazil. So it is visible for both North and South America. As I mentioned earlier, it has an eclipse magnitude of 0.952, which again is 95% of the sun will be fully eclipsed. And the maximum period of annularity during our solar eclipse is about 5 minutes and 17 seconds. No place in North America will see the maximum annularity. We'll get pretty close. We'll be off by about 20 seconds, 20 to 30 seconds short of the maximum. Again, just because that's how orbits work. We're coming at the edge of an ellipse. The full eclipse duration is expected to take about 3 hours from start to finish, if you are close to the center line of the path of annularity. To give a reference, for those who will be in Arizona, Page, Arizona will experience the eclipse at around 8:09 a.m. is when the partial eclipse phase starts, and it ends at 11 a.m. That should be 12 a.m. Excuse me, that's a typo on my part. No, I can't math. 11's right. I need food. So is when the eclipse will finish up at 11, and the midpoint. So this is a rough idea showing the duration of annularity at various cities that lie along the path of annularity. Glen Canyon is also in Page, so that you would expect the annular phase to begin at 9:30. Because this is Mountain Daylight Time, and Arizona is mostly on Mountain Standard Time, so take an hour away from this. Other than that, all of these times are in local time. I think for those of us that are going to New Mexico, there's a couple of really good spots. Like, for example, Albuquerque gets 4 minutes and 42 seconds. And Corpus Christi, Texas gets 4 minutes and 52 seconds, approaching that close to maximum of 5 minutes and 17 seconds. So not far off, only losing 30 to 45 seconds across a lot of the big places. Of course, weather plays a really big factor. You can't see the eclipse if there are clouds. We typically would very much like to avoid that, just as we are doing anything with our telescopes. And so this is a rough chart showing median cloud coverage over the path of totality here in the US. By many accounts, the best portion to see the eclipse will be in New Mexico. It has generally much lower cloud coverage, about 20% cloud coverage along the path of totality, unlike Oregon, which can be anywhere from 50 to 70%. So picking good spots in New Mexico, if you haven't already, what would be the best place to see the full spectacle. In some portions here in western Texas as well. So just again continuing with the path of annularity, excuse me, for this eclipse. This is the North American tract. So it does actually start out over water. So if you are convenient and on a cruise ship, you can see the eclipse much earlier. But I think this might actually not begin for a good time. I think this is cutting it close to when. Oh no, I'm thinking the wrong direction. I'm thinking dawn. Yeah, so since eclipse here in Pages at around 8:09 a.m., it is very early in the morning, so you might just be cutting it close here with the near sunrise over here if you move off towards the west more. And if you are up for a little bit of a trip, this shows the path of the annularity as it finishes up over South America and Central America. So it does get quite a good show over a very wide area. So if you're up for an exotic vacation and probably a drive at this point, most just finding hotels and flights might be difficult during this time. But nonetheless, pretty interesting if you do get to go there. The next eclipse, excuse me, that's a typo on my part, is the total solar eclipse on April 8th, 2024. This eclipse begins in Mexico, and it will end off the coast of Newfoundland, Canada. Excuse me. It has an eclipse magnitude of about 1.05, with a maximum totality of about 4 minutes and 28 seconds. This contrasts to the Great American Eclipse of 2017, which I think was about 2 minutes and 37 seconds of totality. So we're almost doubling if you are close to the center line of the eclipse. The full eclipse is much shorter than the annular eclipse this fall, taking only 2.5 hours from start to finish. For example, Dallas, Texas, which is closest to the center line of the eclipse than some other cities in the U.S. The eclipse will start at 12:23 local and end at 3:02 p.m. local. So very much an afternoon, which means the sun will actually be high up in the sky. So, this is another chart showing various times of totality and the start and end times at various locations along the path. Both of these tables you can go look at greatamericaneclipse.com. That this site does have a lot of other really great eclipse observing resources. So if you are planning something, definitely go check them out. They have some other more detailed maps of the path of totality. I just didn't want to show them here in this presentation just because of time. But for those of us here in the US, it is generally believed that Texas is going to be the place to go. And to give you an idea here, showing the average cloud cover. So if you don't have your passport, Texas specific will be your best bet here and to see the eclipse in the U.S. Maybe a little bit of Arkansas just for general cloud cover, but you're still getting up to the 50% range. For those of you that do have your passport, Mexico will very much be your best bet in terms of apparent cloud cover, with generally a very low amount of clouds overall. If you're looking for good location, other than that, you might get lucky, like we did for the total eclipse in 2017. So this is just a rough guide to help. These two charts of cloud covers are just a rough guide to help with planning if you are trying to make a decision about where to go. Again, weather is fickle, anything can happen. And quick pause for some questions, comments. Anyone want to chime in about the two upcoming eclipses or add anything? Okay. So moving on to eclipse observing. So the sun is really bright, and we shouldn't look at it directly. And we also pretty much don't want to try to touch it. This is just kind of a very quick sense of humor of XKCD. Again, I am a very big fan of this. It's always nice to see interesting ways in which we can compare just how bright the sun is and why we shouldn't look at it directly. This is an excerpt from one of his articles where describing if we wanted, which asks simply, how many fireflies would it take to match the brightness of the sun? And it turns out it is a really big number. Conveniently, about 5. It can be quite large. Excuse me. I need to refresh myself on this. So this portion is asking if we had just a single giant firefly as bright as the sun, how bright would it be? And this single giant firefly would be larger than our solar system. So nuclear fusion is very efficient and very bright. So because of that brightness, you do need eye protection at almost all times during a solar eclipse, with the exception of totality. There are a couple of different ways you can do this. You can go out and buy a pair of eclipse glasses. For vendors, if you are looking for one, I would recommend Starzona here in town. They do sell some that are that will be quite cheap. I think they're about $3 a pair. If you're looking just to buy them online, do not buy off Amazon. There will be a lot of people trying to scam and make making scam filters that aren't actually solar certified or solar rated. If you are looking for a second filter that's online, Thousand Oak Optical will be your best bet. So those two vendors would be my recommendation of choice for solar eclipse glasses. And Thousand Oak Optical also sells high quality solar filters for telescopes and for cameras. If you're looking for something a little less direct, you can also use what's known as a pinhole projector, which is simply just a hole punctured through a piece of paper or cardboard to where you will see the inverse projection, hence its name. And as a general rule of thumb, if you are using solar filters or eclipse glasses, discard them immediately if they are even barely scratched. The sun is so bright that if that one small scratch is enough to ruin your vision, there was to demonstrate, to explain why this is so important to discard, there was a woman during the 2017 eclipse who was using fake glasses, and she now has a permanently burned in image of a partial eclipse in her eye. Very important for proper eye safety. Most solar eclipse eyeglasses use what's known as a Seymour film, which will make the sun appear as kind of an orangish hue. This is giving an example here. And I believe these were no, never mind. For those of us that are trying to photograph the eclipse with a wide angle lens, if you are using a telephoto lens or perhaps hooking your camera up to your telescope, you must use a solar filter or you will destroy your equipment. But if you're using a wide angle lens, like say your phone or a DSLR camera with like a wide angle lens, you do not want to look directly through the eyepiece on the camera. You will want to look through the live view screen instead. This is because the eyepiece is generally just reflecting light coming into the camera body. which is essentially taking a magnifying glass to your eye with sunlight in it. And if you've ever played around with ants in a magnifying glass, you know that doesn't end well. General, again, safety is always paramount when you're dealing with the sun. You can use what's known as neutral density filters. These are not quite, these won't black out nearly as much light as a solar filter, but their effect is basically the same. They just make the sun appear less bright, which is good if you're trying to get certain features and scenery during any of these eclipse phases, which might be more critical for those who are doing like landscape scenes. A neutral density filter will play more effect with the October eclipse, because it happens so early in the morning. The sun will be generally relatively low, giving you some chances for some really good landscape shots of a partial eclipse with background. Unfortunately, that won't be the case for the upcoming total eclipse in April, just because it's going to be occurring much later in the day. It'll be mostly clear of any horizon. So there won't be as unless you're in Mexico right near the start of the eclipse, you won't get as many good opportunities for landscape shots. You also do not want to leave your lenses exposed to the sun for too long unless you're using a solar filter. So this is just because, again, it's a magnifying glass and it'll damage your sensor if left exposed. So if you are taking brief shots, just take, a couple of pictures, cover it up for a while, and then let the eclipse move on before uncovering your camera to take more pictures. That's that only applies if you aren't using a solar filter on your camera. And this is the last slide in the presentation here. I just really like it for the sense of humor, which would simply ask, if you took all of the sun's output of visible light and bundled it up into a laser beam that had a diameter of 1 meter, what would happen when that laser beam hit the Earth? And if you were standing underneath that laser beam, as the comic says, you wouldn't really die of anything in the traditional sense. You would just stop being biology and start being physics. So please be safe during the solar eclipses. And with that, here are some various references if you are interested. And that's it. Thank you for coming. Any questions, comments, things people want to chime in about? I don't see anything in the chat. Quiet for tonight. Cool. Thanks for coming, everybody.
Thanks for that presentation.
I'm going to go ahead and stop.